All right, so welcome to second semester. This is exciting. Um, yeah. So what I'm going to talk about is chemical reactions. Now, chemical reactions there's a lot that goes into them. There's a ton of stuff. This can be a challenging unit in certain spots. Um, this beginning stuff, though, is pretty simple. But then the stuff we do with balancing, that's one of those things that you can ask people about that have been in chemistry class or that took chemistry class, like years ago, and they're like, "Oh yeah, I remember balancing reactions." And some people will say like, "Well, I didn't like that at all." Most people will say that. Then you'll have people that'll be like, "Oh yeah, it's no big deal. It's easy." So there's just this range, and we're not doing that today. But that we will get to that. What we're going to talk about today, this is going to be pretty short. This is just a really brief intro to chemical reactions, the ideas behind them, and yeah. So I'm gonna talk you through like the first two slides or so from the notes. I just want to have this on video. I'll probably do it in class too, but I just also want to have it on video in case anybody wants to refer to this later. So these are just direct printouts from the slides. I thought it'd be easier than trying to screw around with it being like on this, the video on the screen. I figured this would be simpler. Um, and so you can check that out. And then I'm going to walk through the work that I want you to do today. I'm going to do some examples with you. I'll kind of walk you through it with it together. And that'll be that for this video. So, chemical reaction. What is a chemical reaction? Well, it's basically a change that takes place, over the course of time when you have like one substance, and they can be fast, they can be slow, but it's when one substance has their atoms rearranged to form some new substance. Now, in this slide, normally if we were in class, I'd be asking you to read this whole thing, and I'd be like, all right, what's the most important word? Like, what's the most important word present here? And you'd be like, well, I don't know, And then I'd be like, okay, well, and then people would randomly say words, and I included this little bullet point because normally it's not there, but online changing things up to make it better. So anyway, the most important word is rearranged. So a reaction doesn't take place unless atoms are rearranged. That means that bonds are broken and new bonds form between elements or between atoms in compounds. Simply, so like for example, let's say you have water. So you have ice. Ice is solid water, right? So that would be H2O as a solid. All right. So let's say you have solid H2O. All right. And let's say that solid H2O turns into liquid H2O. That's not a chemical reaction. That's not a chemical reaction at all. The reason this is not a reaction is because you have a solid turning into a liquid, but it's still H2O. No bonds are broken, no bonds are formed, no atoms are rearranged. This is just a phase change. This is just ice melting. It's just melting. It's a phase change. A reaction is something that takes place. For example, let's say you have H2O again. Let's say we have liquid H2O again. The liquid is less important in this example. I just, trying to be consistent. And then let's say we have this little arrow. And then let's say we break this down into hydrogen gas and oxygen gas. The process of hydrolysis, where you split water apart. So you can run electric current through water, which is not a good thing to do, obviously, but you can do that. And if you do it right, you will have hydrogen gas created at one end of like the electrical supply, and oxygen at the other end. With the one at the positive, one at the negative. So that's exciting. All right, and you get these things. There's seriously a truck outside right now while I'm trying to do this. That's beautiful. It's very loud. So anyway, you'll have water. It's broken down. So this indicates that bonds are broken. New bonds are formed. You'll notice that you went from H2O to now you have H2 and you have O2. Now some of you might be wondering, well, like what the heck? Why is there two oxygens here and there's only one oxygen here? Well, you would go and you would put these things in front of it to make this all work out. They're called coefficients. We'll get into that part not today at all, but just for the sake of it being accurate. And we'll explain where those numbers came from, all that stuff. But the point is that you have one substance, and The atoms in that substance were rearranged to make new substances, something else, something different. It's very important. So the key word is that rearrange. All right, rearrange is the most important thing there. And if something is not rearranged, then again, nothing happens, or at least I should say, a chemical reaction doesn't happen. So next, the general form of a reaction is shown below. So the general format. Hold on, put my shirt on. The general format is that you start with these things called reactants. So think about this. This is kind of like the before of a reaction. This is kind of like the after, the products. And it makes sense. The reactants are what react. The products are what are produced. All right. Generally, it goes reactants on the left, products on the right. That's a pretty standard format. And then this arrow indicates a reaction takes place usually. Just the arrow indicates like the reaction happening. So that's the basic form of a reaction. All right, that is the basic idea here. Next, when you look at this, you already saw it in the examples that I did just a minute ago. But the basic idea is that some reactions, not always, but a lot of reactions you're going to see are going to indicate the phases of matter of the elements and compounds in the reaction. So I showed you this when we were doing these examples. I wrote down like solid, liquid, gas. All right, those just indicate the phases of the matter. And I just wanted you to have this officially written down somewhere for you, with a very specific reason for one, because I want to talk about what this AQ is, aqueous. That's probably new to you. I assume that you know what solid is. You know solid's solid. It's a solid object. Liquid is something liquid, like water. And then gas is something that is a gas. We've been over the phases of matter. You talk about the phases of matter a lot. But this AQ thing, sometimes in a reaction, specifically usually double displacement reactions, which I'll explain what those are in another video, you're going to see this aqueous thing written. Now, what that means, that's when you have something, a chemical, dissolved in water. So it's kind of weird. So like, for example, if I show you NaCl here, so NaCl, and I write it as AQ. What that means is this. It means imagine you have a beaker of water. All right, so you got a beaker of water. So that's water. Beautiful. That's one of the better things I've ever drawn in my life right there. You should be feel very lucky that you're seeing this. And let's say you have some salt, NaCl. You take the salt, you put it in the water. Well, then you have NaCl in water. You have salt water. One of the most common things on the planet. Maybe the most common thing on the planet. I don't actually know. So you got a lot of salt water. All right. And when you do that, the way you write it as NaCl AQ. So you'll notice that there's no mention of water in this anywhere. There's simply sodium chloride AQ, implying that you have sodium chloride dissolved in water. So that's what the AQ tells you, is that you don't need to actually write H2O anywhere. You're just saying sodium chloride aqueous, it's dissolved in water. There's a way of there's a whole way of measuring and determining how much sodium chloride is in how much water. It's like this concentration unit called molarity, which is something that we'd be talking about in a completely different unit. But just for the basic idea, sodium chloride aqueous, that's what the AQ means. And there's all kinds of things that can be dissolved in water, all kinds of things. This is just the most well-known example, so that's why I use it. So that's the basic idea. That's really basic chemical reactions. You have your beginning, your end, your reactants, your products. You rearrange stuff, and you get new compounds, and the reaction happens. All right. Now that's kind of I try to keep it really simple on the first day of reactions. I try to keep it as simple as possible. Just for the reasoning that I want you to really get this. So what you're going to be doing now is this. So you watch some videos about cool chemical reactions and all this. Now we're just gonna actually write some chemical reactions down. All right, nothing fancy. We're just gonna do this. So basic idea is this. It's kind of weird how I set this up, but I thought it would make sense. So you're gonna take this stuff here, like these things, and you're gonna write the answers So answers go down here from the stuff up here. So what I want you to do, if you have like this stuff, I want you to translate this into a reaction, and so I want you to take words, translate them into a reaction. I want you to take symbols, translate them into a word reaction, and then that same thing down here. I just want you to basically, go through and try this. So what I would encourage you to do now, pause the video and do this. All right, so pause the video and try to do this. Number 4 is kind of hard. The very one at the end here, the one at the very bottom. 4 is kind of hard. So if you can't figure that one out, fine. If you can, congratulations, wonderful. I'll be explaining that one, and then I'm gonna so again pause the video, go and try these, and I'm going to do, a few of them with you. So pause, go do the work. All right. So I'm hoping that you paused the video, that you did the work, tried to do the work. There's no point in just watching this done. If you don't try it yourself, it's not really going to help you. So hopefully you try it yourself. And now I'm going to go over the answers. So yeah, let's take a look at this. So like solid calcium reacts with. So what I'm going to do, I'm going to write it down here. So it says solid calcium. So we're going to write Ca. We're going to write the element Ca because it's calcium, and it says it's solid. So I'm going to put a little S there. And it says it reacts with. So that's going to be plus sign. Reacts with means it combines with. Solid sulfur. So I'm going to write S like that. All right, and then it says to produce. On this S, these S's are because it says they're solid, so I'm writing the S's there. So the produce, like when you're reading this, when you're doing these examples, you're going to want to basically think like, okay, so anything where it says like to produce, to make, to create, stuff like that, like that indicates the reaction is happening, that's code for draw the arrow. And then it says calcium sulfide, so to produce solid calcium sulfide. So to do this, now this involves going back to writing formulas properly. So when you're doing chemical reactions, if you don't write the formulas properly, then it's not going to make sense. So that part's kind of important. So like calcium sulfide. So to write this formula correctly, you got calcium. Calcium is a positive 2 ion. So we got to go back to all that. All right. Sulfur is a negative 2 ion. It says it's calcium sulfide, that's sulfur. All right. Let's see if I have one of those ions floating around this mess over here. So I thought that would be useful to show you. But for the sake of the video. I'm not going to use it. So you can just look at a periodic table. Oh, there it is right there. So again, if you don't remember where these are coming from, so like calcium is +2. So in this ion chart, it's the thing I told you, it never goes away. It's important. And then sulfide, sulfur, it's -2 right there. So calcium sulfide. So when you write this, remember you crisscross. So you'd end up with Ca2S2. But in this situation, you would just simplify to CaS. So you would write CaS, and then it says it's solid. So you'd write a little S down there. So there you go. That's your answer. Now I'll do the next one. So next it says hydrogen gas reacts with fluorine gas. Now, this is an important time to think about the diatomic elements, so we'll get into that for just a second. Well, actually, maybe we'll save that for the next one. No, maybe we'll talk about it now. But there are some things that, and this is kind of important. So we'll do this right here. This is as good a time as any. So there are 7 elements that are called diatomic elements. All right. So you should watch this hopefully. Diatomic elements they are naturally found bonded to themselves. as a gas. All right, so that's H. So that's H2. And I'll just show you. There's a really easy way to remember this. So it's hydrogen. Hydrogen's kind of its own deal over there. But then over here, it forms a little 7 over on the table there. So you got nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All right. So hydrogen, then nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So these 7. So what that means is that whenever you encounter them, whenever you see them, like in a reaction, is described as a gas, you got to write them with a 2 after it. So, for example, hydrogen gas. So you're not just going to write H, you're going to write H2 because hydrogen is diatomic and it's a gas. So you write H2, you put a little G there. Plus fluorine gas, so it'd be like F2 with a little G because again, fluorine's diatomic. Says it's going to produce, so you're going to write a little arrow sign, hydrogen fluoride gas. So that's just HF. It's not diatomic because even though those things are diatomic separately, when they're combined in a compound, that doesn't matter. The diatomic thing only matters when it's an element by itself, when it's a lone element by itself. So in this case, H is +1, F is negative. Here, we'll just write negative. And they crisscross to be HF, 1 to 1, works out fine, perfect. And it says it is a gas, so you put a little G down there. Now, some of you might be wondering, you're like, well, wait, what about these 2's? Why are these 2's not over here? And in reality, you will be putting a big coefficient here in the next class period, so tomorrow or whenever tomorrow is online. And you'll understand that there's 2 of these, and that makes it all work out. But for right now, you don't have to worry about that just yet. So the rest of these you're going to go through, do the same thing. C is going to be the same thing. I'm not going to write it out though, or I can just write it out, but I don't need to. I won't give some grand explanation on it. So metal solid reacts with zinc chloride aqueous to produce solid zinc plus aqueous chloride. So that's what C should look like. The most important thing is that you write these compounds properly. You just got to make sure that when you're doing the crisscrossing that you make sure you do that. Make sure you account for the charges. Refer to this if you need to, but it's all there. And then for these 2, I'm just gonna say them in words. I'm not gonna write it all out. So for A, you would have carbon disulfide. Liquid carbon disulfide reacts with oxygen gas to produce carbon dioxide gas and sulfur dioxide gas. So that'd be good for this one. Then B, you could say aqueous sodium chloride reacts with aqueous silver nitrate to produce sodium nitrate, aqueous sodium nitrate, and solid silver chloride. All right. Now, 3 is pretty much the same as those above. You're just translating this. This is almost just like practice, where you're basically just writing formulas more than you're really practicing writing out chemical reactions at this point. But so all right. And then last but not least, we have number 4, which I said was kind of difficult, and yeah, it kind of is. So it's basically you're trying to get a reaction out of this, and it says one way to test the salinity of a water sample is to add a few drops of silver nitrate solution with a known concentration. As a solution of sodium chloride and silver nitrate mix. So right there, sodium chloride and silver nitrate mix. Now, key phrase here is, because you're thinking about what is the phase too, and you're like, oh, solution. Anything that's a solution is aqueous. So if you ever see the word solution, that's code for it's aqueous. All right. So you'll basically be saying sodium chloride aqueous plus silver nitrate, aqueous, and then this is Ag is +1, nitrate's -1, so that works out there. And then it says, as the solutions mix, a precipitate of silver chloride forms and sodium nitrate is left. So this precipitate thing, that's a new thing for you. So have you ever seen the word precipitate? Up spelled wrong. Word precipitate. That means that something is a solid. Precipitate, it's not rain, it's not precipitation. It just means that something is a solid. So you would show, and the precipitate concept will be explained more in depth a little bit later. So you have silver chloride, so you would just say AgCl solid plus NaNO3 sodium nitrate is left in solution, meaning it is aqueous. And if you notice, that's actually this exact thing from there, from B. A few things to know. Reactions don't matter in terms of, like, if I wrote AgNO3 first and then NaCl, it doesn't make a difference. Like, it doesn't matter which thing is before the plus or after the plus. That doesn't matter. Or same thing over here. It doesn't make any difference what's before or after. Or, like, just the order of stuff doesn't matter on the sides. The only thing that matters is that they're on the, the correct side of the arrow, on the reactant side of the product side. That's the only thing that really makes a big difference. All right, so there you go. Let me know if you have questions.